Today we will move into superposition, and we will talk about superposition now. So in the GIF, again from Flipping Physics, link in the description, you can see two sort of interference. The idea of superposition is to answer the question, what happens when you have two waves meeting each other? Do they collide? Of course not. They do this thing that we call superimpose. So if you look at the top GIF diagram, it's an example of a destructive interference. You have two waves traveling towards each other, and when they meet, they cancel out. Then they travel back in the opposite direction. So you can see the wave that is coming from the right, it was positive A, on the upwards, it hits to the left. Whereas constructive interference, you have two waves coming together, becoming something big, and then traveling back in the opposite direction. So the wave, right, when they meet, they build each other up, and then they continue their journey. All right, so we're going to write that down, principle of superposition. So basically, we're trying to answer what happens when two waves meet. Okay, it is important to know that when they meet, they carry on their journey. Okay, so right now, when two or more waves meet at a point, the resultant displacement is the sum of its individual displacements. So for example, if you're talking about the constructive interference, you have two or more waves meeting at a point, okay, and the resultant displacement is the sum of the individual displacements. Normally this definition is 2 marks lah. Okay, so you should say that they are meeting. So I'm going to draw two waves. Waves 1, let's say amplitude A, going to meet with wave 2, let's say also amplitude A, and where they meet, you will get 2A. Okay, and then they will leave each other. They meet, they create 2A, they leave each other. All right, so this is an objective question, okay, just to give you a rough idea. There are 3 waves shown in each diagram with the same amplitude and frequency, but they have a slight phase difference, okay, and we will add them together to give a resultant wave, and we want to know which one is 0. So since there are so many waves and it looks a bit confusing, I'm just going to highlight each wave with a different color. And because this can be incredibly boring for you because you're watching and not really highlighting, I'm speeding this part up. Okay, so as you watch the wave show, once again, I would like to explain, if you have positive A in this direction, meeting positive A in this direction, they meet, become 2A, and then they travel away. Positive A in one direction, negative A in the opposite direction. When they meet, they flatten out, and then they travel in the opposite direction, cancelling out. All right, so by magic, now we can look at the 3 waves and see which one will give us 0 when we add them up together. Let's look at C. At C, right, there are so many places where all 3 waves are positive, like I mark out in the line. So there's no cancelling, C is out. Same thing for D, that position, all 3 is positive. D is out. What about B? If B, right, you look at certain points, blue is 0, yellow is 0. So the only resultant is purple, which is also not 0, so it cannot be B. So by process of elimination, which is the best way to do objective, the answer is A. But we can double check. If you look at the lines where I draw, yellow and purple will cancel out blue. At the second line, purple and blue will cancel out yellow, and so on and so forth. So the answer would be A. All right, so that's the idea of superposition. So we're going to rely on the idea of superposition to set up this thing called stationary wave. So the condition for stationary waves are 2. Number 1, obviously if there's meeting, we need 2 waves. Okay, so there are 2 waves with the same frequency, wavelength, and speed. Also the amplitude have to be the same. In other words, the waves have to be identical, and they have to be traveling in opposite direction so that they can meet. All right. So right now, I'm just going to show you a few setup to make this possible. As you can see, on the left, there's a vibrator which will create a string wave, and the wave will travel towards the wall where it will be reflected backwards. So if the reflection is perfect, we can assume that the incident and reflected wave is the same. Just like the signal generator or a loudspeaker will create an incident wave which reflects at the end of the air column. And you have a microwave source with an incident wave and it reflects at the metal reflector. Okay, so the idea is you have one and then the reflected one will come and they're in the opposite direction. Okay, so we're going to talk a little bit about the explanation. Okay, because this part they can ask you to, in 2 to 3 points, explain how stationary waves are formed. So to explain the formation of stationary wave, we will start off by saying that a wave from a particular wave source. So if you look at my 3 examples, all the wave sources are on the left. So you have to be question specific, like wave from the vibrator or wave from the signal generator, travel towards and is reflected at the wall or the end of the air column or the reflector. Okay, so be specific to the question. All right. And number 2, you have 2 waves now. You have the incident wave and the reflected wave. So the reflected wave and incident wave, okay, very important. What do? They overlap or they meet or they superpose. Do not use the word interference. Okay, interference is a very specific thing. We will talk about this later. Okay, so since the reflected wave, so mention how it fulfills the condition. Reflected wave and incident waves have the same frequency, wavelength. I miss out this point, frequency, wavelength, and amplitude. Okay, so stationary waves are formed. I will add in the amplitude in the final version of the notes because I ain't going to record this again, child. All right, anyway, and normally the explanation is 2 to 3 marks. The condition is also 2 to 3 marks. Try past years lah. You will get a better idea. All right. So right now we're gonna carry on a bit, and I want you to look at this formation of stationary wave. You have 2 waves, the blue and the red, traveling in opposite direction, and when they meet, when they align nicely, you form the black wave maximum. When they are opposite of each other, you get the black wave as cancelling out. So if you look at the black wave, right, it is as if it is not moving. It's just going up and down, up and down. The energy is trapped, hence stationary wave, because the black wave doesn't look like it was moving. So we're going to try to visualize this, and this drawing will probably take us some time. So some of the parts I actually fast forward 8 times. Ooh. So I'm just going to start with waves. Okay, just want to remind you that the condition for stationary wave is that they have to be traveling in opposite direction. So I'm just going to draw one wave first. Let's say now the time t is equal to 0. And it is at this point where I make a labeling mistake because the x-axis is supposed to be x and not t. I will correct it eventually. So let's say this blue wave is traveling towards the right. Okay, I'm going to take a place marker for the wavefront. This is not a wave particle. It's just a marker or a reference point. So let's say it travels by a quarter cycle towards the right. Okay, so I'm just going to fill up this wave. So you can see it's quite evident that the wave has traveled a quarter wavelength towards the right. And then I will keep moving the wave by quarter wavelength for every quarter cycle, because 1 wavelength for 1 cycle. Okay, so here I am filling it in, occasionally erasing because I want it to look nice. I draw nicer on the whiteboard, just don't have it now. Okay, so ta-da! And as you can see, I'm filling in the time, and this is 3t/4. So every quarter increment. Okay, so every quarter we bump 1 box, t/4. This is where I noticed that, hey, I labeled wrongly, and this is actually lambda. Okay, and the reason why I notice I labeled wrong is because I want to point out to you that when the time is exactly 1t, the yellow dot reference point, not a wave particle. Okay, once again, the wave particle only move up and down. It doesn't travel together with the wavefront. So the reference point or the wave profile has traveled 1 lambda distance after a period t. Okay, so I'm just drawing in increments of every quarter cycle. All right. So the wave profile would have traveled by lambda. Okay, and of course the vibrator keeps vibrating. The wave source keeps producing wave source. So we're gonna have to complete the wave pattern. Okay, so we're just drawing it moving every quarter cycle and then completing the front part. The purpose of drawing this is to help you understand the idea of superposition and also how it forms the stationary wave. Okay, so I'm not quite sure what happened here, but there we go. So you can see now I'm connecting all the waves. Okay, so there we go. All right, so this is one waves. Okay, and we are hopefully going to draw the other wave that is traveling in the opposite direction. Okay, so I'm tracing out the other wave in red. So let's start off this wave at the exact same position. It doesn't have to be, but it's just easier this way. So the red wave is traveling in this direction, towards the left. So I'm just going to take a reference point. As you can see, the blue point is the reference point in highlight. Okay, and I'm going to very quickly move the wave by a quarter cycle. So by a quarter cycle, the wave should be here. I can only draw in one direction, my hand, because I'm right-handed. All right, and then we will continue moving the red wave. And you notice that the red wave will overlap the blue wave in every half a cycle. Okay, so there's actually an editing problem that I have right now with video editor, which I kind of don't know how to fix it. So we'll just deal with it for now. All right, so we're going to continue moving the red waves. If you're drawing with me, which is the ideal way to learn, you can perfect your sine curve. Make sure your sine curve look like sine curve, not like two hemispheres on top of each other, which is just weird. Okay, so once again, we're moving the red. So it will take turns to go out of phase and in phase, and then out of phase again. Okay, there we go. So now we're going to draw the resultant wave. All right, after we're done. I think the problem with the editing is the splitting. So we're going to total up both the red and the blue graph to give us the green graph. So blue A plus red A will give us 2A. A plus A is 2A. Negative A plus negative A is negative 2A. So the second cycle, you will get negative 2A. All right. And if we move up, we will get positive 2A. We're moving up towards positive 2A, back down to negative 2A. And then finally, 0 plus 0 is naturally 0. So you kind of get like that big black color curve. I'm trying to make sure that the amplitudes are the same. All right, so I'm going to label the amplitudes now. This is 2A, negative 2A, A and negative A respectively. Okay, so now if you look at the red and blue, they perfectly cancel out after a quarter cycle. So you just draw a straight line. Everything is cancelled. 2020 is cancelled. So these two waves cancel. But don't worry, after a quarter cycle, they build each other up again, just in the opposite phase. Okay, so what was positive A is now negative A, and what was negative A is now positive A. But you get this maximum 2A situation happening. All right. Okay, and then the next quarter cycle, they cancel out. The next quarter cycle, they start again. By the way, right, the thing about waves is it's easy if you can visualize, okay? So a lot of us, we struggle with visualizing. So I find GIFs quite helpful. So when you do a question and you find it hard to actually decide stuff like phase angle or relationships, just Google the GIF, all right? So right now you can see there are certain points where the green graph is always 0, and we call them nodes, N-O-D-E-S. So nodes are places with zero displacement. The particles don't have to move. All right, so all these are nodes, as you can tell. Okay, and there are also places where the particles have to move a lot, from positive 2A to negative 2As, and we call those particles antinodes. As you can see, I'm labeling them right now, and then you get that na situation happening. So as you can see, maximum 0, maximum opposite direction 0, maximum opposite direction 0. So you create the black wave as the result, and oftentimes you will notice that it's as if the black wave is not traveling, because the black wave is the result of the blue and the red. Okay, so right now we're going to compare progressive and stationary wave. Okay, progressive is just the blue wave alone, and you can see the blue wave will travel. Okay, so the wave profile and with it the energy will travel from one point to another point, normally through a medium lah, unless it's light or microwave, which is also light. Everything is light. Don't you think it's a conspiracy after watching lecture 1.3? Anyway, the energy will travel from one point to another for progressive wave, hence it progresses. Okay, and for stationary wave, I'm just going to draw a rough drawing here for you. Okay, now stationary wave, because it is in place and we are not in Hogwarts, so I cannot animate the GIF for you lah. But I'm just going to draw a dotted line to show the alternative maximum position. Okay, but there's only one wave. All right, so in this case, the wave profile appears to stay in place. Okay, so it's not going to move anywhere, and the energy is trapped. Okay, it's trapped between two nodes, and I will show you a video of that later. All right, so two nodes are here. Actually, in this, if you count properly, there are 4 nodes. Okay, and also at the same time, let's label the antinodes. At least I think that's what I'll do later. We're now going to compare the amplitude. The amplitude is constant for all particles. So if let's say the amplitude is 4, all particles will take a different time to reach 4 cm, let's say. So it reach maximum displacement at different times. Okay, again, if this is not clear, you can ask me during class. Okay, whereas the amplitude for stationary wave, okay, it varies from 0, which is the nodes. The nodes have no amplitude. Okay, to maximum, which is the antinodes. The antinodes have an amplitude of 2A, or double the overlapping waves. Okay, and then it goes back to 0. So from node to antinode to node. So 0 to maximum, back to 0. Okay, this one is between 2 consecutive nodes. All right, and then they reach maximum displacement at the same time. So when I say reach maximum displacement at the same time, it means that if A reaches maximum displacement, okay, so I'm labeling the A right now, all the points beside A will also reach maximum displacement. And A here is antinode lah. I'm just doing the scientific thing where I label my symbols. All right, what about period and phase relationship? So if you consider a wave particle and its neighbor on a progressive wave, they never travel up and down at the same time. If I'm on a progressive wave, the next person that is traveling at the same way as me, or same phase relationship as me, is lambda away. Whereas for stationary wave, if you remember the black wave, they go up together, they come down together. They go up together, they come down together. And because of this, the phase angle is 0. All right, because the phase angle is 0, all your particles, okay, to the next adjacent particles is out of phase. So I'll explain this a bit to you. So you can see, right, I'm going to label a few points, because between 2 n and n, let's say point P and Q, they travel up and down at the same time. Okay, and then let's say from S and T, they travel up and down at the same time. So in phase means they travel up together. P and Q is in phase because they are between 2 nodes, whereas S and T are also in phase. Antiphase will be P and S. Okay, P and T also can. Q and S also can. Okay, as long as you are taking the neighbor's particle. Okay, when I say neighbor, I mean the neighboring nodes. This is what I mean by to the next adjacent node is out of phase. Because one side will go up, the other side will come down. Okay, hopefully later when we look at waves on the string in an experiment, it will be clearer to you. Okay, so when we look at wavelength, as mentioned just now, wavelength is the distance between two particles that are in phase. They also have to be adjacent or consecutive. That means the next particle that is in phase. It might not be next door. Okay, so for this one, if you want to find lambda, you will notice that n and n is lambda over 2. A and A is also lambda over 2. Okay, so I'm labeling that now. N to n is lambda over 2. And one A to the other A is lambda over 2. Okay. I'm just gonna write that down. In fact, this one is very useful. That's why stationary waves are pretty easy to do. Because there's no equation to memorize. If you get how the wave is shaped, you can deduce whatever information you want from the shape that is drawn for you, or you can draw the shape that is required from the information that is given. So 2 times adjacent nodes or antinodes, because n is lambda over 2, or AA is lambda over 2, and because of this, n to A is lambda over 4. Okay, so yeah, so this is a YouTube video. I will again link it below of how a stationary wave is formed in the pool. So at the end of the pool, there is a vibrator that will send the water wave towards the reflector, which is closer to the camera. Okay, this yellow thing is a reflector. So right now, the waves you can see the wave is still traveling. So this part of the wave is still progressive because it has not been reflected yet. So progress, okay, and then now it has begun to incident or overlap. And you can see after a while, it's as if the wave is no longer moving. It's just sloshing about, up, down, and they slosh synchronously one. You have 4 going up at the same time, and then the neighbor go down. And then they take turns. You go up, they come down. So they kind of travel like this with their neighbors. Quite cool, right? So if you look at it, it's as if the wave didn't move. All right? And the energy is trapped, and then you can build up to quite high. Okay? So I'm just going to fast forward a bit so you can see a close-up. Okay? So you can see it's as if the wave is not traveling at all. It's just sloshing. The water is just sloshing inside the pool. So yeah, stationary wave. Okay? And I'm just going to fast forward and let you stare at it a bit. So as you can see, more energy and momentum is being built up, right? And also, if you stare at it, right, you notice that all the wave between 2 nodes rise together, come down together, rise together, come down together, rise together, come down together. Okay, so that is your stationary wave. Okay, isn't it cool? Sloshing about. I will see you in the next lecture on standing waves on strings. Bye-bye.